January 12, 194, the West Yard of Fisher Body Plant No. 2, Detroit, Michigan. Outside, the temperature measured 19 degrees Fahrenheit. Steam rose continuously from vents along the foundry wall. Inside the assembly shed, arc welders illuminated the steel hulls of M for Sherman tanks under construction. Each section advanced by crane, then lowered onto support blocks for final alignment. Production foremen carried clipboards marked U.S. Army contract, Ordnance Department. Posters along the wall displayed the slogan, "Work wins wars." The shift siren sounded at 7 o'clock hours. More than 600 men reported for work, divided between welding, fitting, and inspection crews. Every operator wore standard-issue overalls, leather gloves, and protective goggles issued by the Safety Bureau. Noise levels exceeded 100 decibels near the welding lines, requiring communication by hand signals. Electric power for the arc systems drew directly from the Detroit Edison substation. According to plant records, each completed hull required more than 2,000 linear inches of continuous weld. Observers from the Ordnance Department monitored efficiency tests that morning. Their clipboard notes indicated recurring misalignment of the side plates and turret ring assemblies. Average correction time per hull exceeded 45 minutes, delaying crane turnover. Steel shortages prevented expansion of production lines, and the management sought process improvements rather than additional machinery. Every delay translated into fewer tanks delivered to Army depots in Illinois and Ohio. At 8:15 hours, a maintenance technician from the machine shop approached the welding foreman. His name was Charles Red Whitaker, age 41, formerly employed at Great Lakes Steel. Whitaker had spent 15 years repairing press fixtures and alignment tools before joining the tank program. He carried a hand-drawn diagram rolled inside a cardboard tube marked hull jig, adjustable concept. The drawing showed a simple steel frame with sliding clamps capable of holding multiple armor plates simultaneously. Unlike the fixed templates then in use, Whitaker's frame could be adjusted with threaded bolts and locking pins. The foreman, identified in the plant report as J. L. Morgan, authorized a limited trial on hull number 3276. Welders repositioned the front glacis and side plates using Whitaker's adjustable jig. Time to fit was reduced from 45 to 17 minutes. Subsequent weld inspection passed without rework. Plant Superintendent Harold Lyons ordered a second test to verify repeatability. Results confirmed consistent alignment within a tolerance of 1/32 of an inch. By 9:40 hours, the Ordnance observers documented the experiment as notable for simplicity and repeatable precision. Whitaker requested scrap steel to fabricate 2 larger versions capable of holding full-length hull assemblies. Management approved the request under Maintenance Authorization 114B, filed that afternoon. The original jig, still covered in welding residue, was photographed by Army Signal Corps personnel for record inclusion. The photograph shows Whitaker standing beside the frame, his name tag barely visible under a layer of soot. The following week, word of the device reached the War Production Board's regional liaison. A brief memorandum described it as an improvised mechanical fixture enabling increased throughput without capital expansion. It marked the first documented instance of a worker-devised tool directly affecting national tank output metrics. From that point, the incident was recorded not as a local improvement but as a wartime innovation with measurable industrial effect. By February 1942, the United States had been at war for only 2 months. Army ordnance projections called for 15,000 medium tanks within the calendar year. Existing industrial capacity could deliver less than half that number under current labor and material constraints. Expanding facilities required months and additional steel, both already allocated to shipbuilding and aircraft production. The Detroit Tank Arsenal, operated by Chrysler, served as the central node of American armored output. Supporting plants such as Fisher Body, Pressed Steel Car Company, and American car and foundry handled subassembly fabrication. Each relied on heavy welding equipment and precise jigs to ensure dimensional uniformity between contractors. The principal challenge lay in maintaining alignment tolerances across hundreds of separate components produced at speed. Reports from the Army Industrial Division noted recurring bottlenecks caused by fixture inflexibility. Every variation in plate thickness required recalibration of the entire jig assembly. When rework occurred, cranes and labors were idled, causing cascading production slowdowns. No additional cranes or welding stations were available, and wartime directives prohibited new plant construction without Washington authorization. Under these limits, any improvement in fixture adaptability translated directly into production gain. Charles Whitaker's adjustable jig represented a solution from within the workforce itself. He designed it using salvaged structural steel, threaded rods, and surplus bolts from machine shop inventory. The design allowed a single operator to reposition the jig for different hull configurations in under 5 minutes. Traditional fixed jigs required entire teams to adjust, often taking over an hour between hulls. His method replaced complex alignment gauges with simple calibrated markings etched onto the sliding arms. The War Production Board's engineering section evaluated similar concepts but found none as immediately practical. Whitaker's frame could be duplicated in any shop equipped for basic metal fabrication. It required no precision machining, castings, or new tooling orders from suppliers. The idea aligned precisely with federal policy emphasizing reuse of existing materials and reduction of downtime. By March 1942, field inspectors circulated preliminary performance data from 5 facilities testing prototype versions. The data recorded a 47% reduction in welding preparation time and a 29% reduction in total assembly duration. Output per shift increased accordingly, without additional labor or energy consumption. Internal memoranda classified the improvement as a process multiplier, a term used for modifications that raised production efficiency without expansion. In economic terms, the jig's cost-benefit ratio exceeded 80:1. Each frame consumed less than $60 in materials yet yielded hundreds of additional finished tanks over its service life. Plant accountants verified this figure through quarterly ordnance audits. For comparison, equivalent output gains elsewhere required expenditures exceeding several $1 million in new equipment. The effect extended beyond Detroit. The Army Ordnance Department issued Technical Bulletin TBR 42-117 recommending Whitaker's fixture standardization across medium tank contractors. Engineering copies of the original diagram were reproduced and distributed to facilities in Pennsylvania, Illinois, and California. The language of the bulletin described the design as operator-devised, field-tested, and immediately implementable. This wording emphasized that the improvement originated from the floor, not from engineering headquarters. In less than 2 months, an improvised device built from scrap steel had entered official ordnance documentation. It demonstrated that small technical interventions could match or exceed the impact of major capital expansion. By the end of the first quarter, American tank plants began measuring productivity not in labor hours, but in fixture efficiency ratios. The Whitaker jig became an early example of wartime industrial adaptation guided by necessity rather than formal design. By April 1942, systematic testing of the Whitaker jig was underway at 3 major plants, Fisher Body in Detroit, Press Steel in Chicago, and American Car and Foundry in Berwick, Pennsylvania. Each facility operated under the same Ordnance Department oversight, using standardized record sheets for time, precision, and defect rate. These tests were supervised by engineers from the Detroit Arsenal Development Section. Their objective was to quantify measurable efficiency improvements under identical working conditions. At Fisher Body, average alignment time for a Sherman hull declined from 42 to 18 minutes per unit. At Pressed Steel, the time was reduced to 21 minutes. In Berwick, despite smaller welding crews, the time stabilized at 19 minutes. Across all locations, dimensional deviation dropped below the Army's maximum tolerance of 1/16 of an inch. The reports also confirmed a consistent reduction in rewelds and corrective grinding. Investigators found that the primary advantage came from the jig's self-centering mechanism. Each frame used for threaded bolts positioned at equal distances along a steel crossbeam. When tightened, they applied even pressure, ensuring the armor plates remained square without manual adjustment. Traditional fixed jigs required spacer blocks and hammering to achieve the same result. The new system eliminated the need for impact alignment, reducing both noise and material fatigue along the weld seams. Welders reported a secondary benefit. Because the jig held the plate edges firmly, they could run longer continuous welds without interruption. This improved weld penetration and decreased the risk of porosity, a common cause of later cracking. Inspection records showed defect rejections fell from 7.4% to under 2% within 6 weeks of adoption. Each hull required approximately 1,200 pounds of welding rod, and lower defect rates directly conserved scarce consumables. The Ordnance Department's Industrial Engineering branch performed statistical verification using production logs. Charts indicated a 52% increase in completed hulls per shift at plants using the Whitaker system. At the same time, electric power consumption per hull dropped by 18% due to shorter weld durations. Material use per unit remained constant, confirming that improvements derived solely from process control rather than supply increase. By mid-May 1942, the National Research Council's Division of Engineering drafted an internal memorandum summarizing findings. The report identified 3 key innovations: the adjustable clamping system, the sliding crossbeam, and the use of existing scrap steel for fabrication. It concluded that these elements together formed a new class of field-devised alignment fixtures. The report recommended their deployment not only for tank hulls but also for ship bulkheads and aircraft fuselage segments. A visit by Colonel Richard Summers, head of production efficiency for the Ordnance Department, confirmed the results on site. Summers' field log recorded, "Whitaker device achieves mechanical alignment previously thought unattainable without precision machinery. Recommend full authorization." Following his inspection, the Detroit Arsenal Engineering Board approved the design for general issue under Specification E-1057A. Blueprints were standardized and distributed through the War Production Board's Technical Data Service. By June 1942, plants in Cleveland, St. Louis, and Los Angeles began constructing their own versions using locally available materials. No 2 jigs were identical, but all adhered to the same functional geometry. Production supervisors reported that adaptability made them suitable for other armored vehicle types, including the M10 tank destroyer. Photographs from the period show multiple crews working simultaneously, each hull supported by its own adjustable frame. Within 6 months of its introduction, the improvised jig had evolved from a workshop experiment into a nationwide manufacturing standard. It demonstrated that process-level discoveries could yield industrial transformation without bureaucratic delay. For the War Department, this success provided measurable proof that innovation from the factory floor could directly influence war output statistics. From that point forward, internal circulars began requesting operator-originated mechanical proposals for evaluation, an unprecedented reversal in military procurement culture. By July 1942, production figures across the tank program showed a marked inflection. National Ordnance summaries indicated that medium tank hull completion rates had doubled compared with the March baseline. Factories using the Whitaker jig recorded the most pronounced gains, often exceeding projected output by 30 to 40%. Inspectors attributed the rise to process stability rather than labor expansion or additional equipment. In official correspondence, this phenomenon was referred to as capacity realization through mechanical simplification. Plant foreman reported that alignment delays had virtually disappeared. A single welder could complete full-length seams without repositioning assistance. Turnaround between hulls dropped below 20 minutes, compared to nearly an hour before jig adoption. This allowed each crane bay to handle 2 additional hulls per shift without overtime. In practical terms, Detroit alone produced over 100 additional hulls in July without increasing man-hours. The Ordnance Department's Production Engineering Division confirmed these findings in their mid-year audit. Compiled from 24 participating facilities, the audit listed 9,780 hulls completed versus 4,830 in March. Statistical correlation showed a direct link between facilities reporting jig deployment and accelerated completion rates. No other single modification or tool achieved comparable impact within the same time frame. The underlying realization was industrial rather than mechanical. For the first time, the U.S. Army recognized that efficiency could advance without centralized redesign. Whitaker's device proved that technical progress did not always originate from laboratory or management directives. Instead, practical field observation, the understanding of a worker confronted by daily obstacles, could yield national effect. This shifted production doctrine from top-down engineering control to bottom-up feedback analysis. In late July, the War Production Board convened a technical roundtable in Washington to assess replication potential. Participants included representatives from Chrysler Defense, Baldwin Locomotive Works, and the U.S. Maritime Commission. Meeting minutes show Whitaker's name listed under originator, though he did not attend. Discussion centered on adopting similar adjustable fixtures for ship keel alignment and turret mounting stations. The consensus favored extending the principle to any assembly requiring repeated precision without retooling. Following that meeting, the board issued Directive 1446, adoption of adaptive jigs and fixtures where feasible to increase throughput. The directive cited Whitaker's case as empirical justification. Plant inspectors were instructed to identify local opportunities for similar field-devised solutions. Within weeks, hundreds of reports arrived detailing improvised clamps, rotating tables, and mobile supports inspired by the same principle. The board catalogued these under a new section titled Shop-Originated Devices with Quantified Output Impact. By August 1942, production strategists began referring to Whitaker's contribution in broader terms. Economists from the Office of War Mobilization labeled it an example of process elasticity, the ability to expand production within fixed capacity. This insight redefined how industrial plants calculated efficiency potential. Instead of measuring productivity solely through labor or machinery, they began analyzing adaptability as a quantifiable resource. The adjustable jig, a simple mechanical frame, had introduced an entirely new performance metric to American war industry. On the shop floor, its value was evident. Welders completed hulls faster, inspectors found fewer faults, and managers reported consistent throughput under constant resource levels. The lesson was technical but carried administrative weight. Efficiency depended not only on capital investment but on process understanding. In official archives, the Ordnance Department labeled the Whitaker improvement as verified, replicable, and sustainable. By the close of 1942, that classification became the benchmark for all subsequent wartime mechanical innovations. By September 1942, the statistical impact of Whitaker's jig had entered formal production summaries distributed to Congress and the War Production Board. Appendix tables in the Tank and Armored Vehicle Progress Report, Q3 1942, listed fixture adaptation as a primary factor in the doubling of armored hull output. Within 6 months, the combined manufacturing output of Detroit, Chicago, and Berwick had exceeded pre-war capacity projections by 118%. All increases were achieved without the addition of new assembly halls or machinery procurement. The Ordnance Department's Efficiency Division categorized the Whitaker system as a Type 1 non-capital multiplier. This term described improvements producing more finished equipment per man-hour, without raising material or power consumption. Further analysis showed that these devices shortened cumulative welding time across all tank plants by approximately 1.6 million labor hours in 1942 alone. Converted into tank units, the savings equaled roughly 3,200 additional hulls. The strategic significance was immediate. By the autumn of 1942, American forces in North Africa required large quantities of M for Shermans for Operation Torch. Arsenal records confirmed that all vehicles shipped for the landings originated from facilities using Whitaker-type fixtures. Without that acceleration, the deployment schedule would have required postponement until early 1943. Thus, a device designed on a factory floor contributed directly to the readiness of frontline armored divisions. The National Defense Advisory Committee later correlated these findings with parallel increases in spare part production. Faster hull completion allowed redistribution of welding personnel to turret fabrication and final assembly. The resulting coordination reduced bottlenecks across the entire manufacturing chain. Industrial planners referred to this phenomenon as horizontal propagation, where one process improvement generated indirect gains in others. By December 1942, the tank program achieved near-synchronous completion rates for hulls, turrets, and powertrains. Quantitative summaries compiled in early 1943 validated the overall industrial transformation. Total American tank production had reached 24,997 units, compared to 4,052 in the previous year. Internal memoranda identified fixture adaptability, labor training standardization, and component interchangeability as the three decisive factors. Of these, fixture adaptability required the least investment and yielded the highest relative return. Whitaker's invention became the canonical example cited in training manuals distributed to new war plants. The broader industrial implication was philosophical as much as mechanical. Traditional management models placed innovation within engineering departments. Wartime conditions displaced that hierarchy. The Whitaker case demonstrated that analytical observation at the operational level could rival formal design bureaus in national effect. It altered the structure of production research, leading to the creation of the Shop Practices section within the War Production Board in 1943. This unit's purpose was to collect, verify, and distribute worker-devised solutions capable of replication. By mid-1943, the Army Industrial College introduced the case into its curriculum on wartime production logistics. Lecture notes defined it as an instance of non-capital throughput enhancement achieved through geometric fixture adaptability. Cadets studying industrial management were instructed to model similar mechanisms for peacetime manufacturing efficiency. In the archives of the War Department, this terminology persisted throughout the decade, long after the tank lines had closed. The data confirmed a measurable legacy. American armored output surpassed Axis totals by a ratio exceeding 3:1 by 1944. Industrial historians later traced part of that advantage to the culture of technical improvisation fostered during this period. Whitaker's jig had not only accelerated a process, it had exemplified the conversion of individual insight into institutional methodology. From an improvised frame in a Detroit workshop emerged a systemic model for wartime production efficiency, durable, reproducible, and quantifiable. By January 1945, the War Production Board compiled its final summary of field-derived manufacturing innovations. Among hundreds of entries, Whitaker's adjustable jig remained listed under the category Most Effective Operator-Devised Tool. The accompanying report credited the device with a sustained 40% productivity increase across the national tank program between 1942 and 1944. No comparable process change achieved similar results without formal engineering sponsorship or new equipment orders. Postwar auditors from the Army Service Forces confirmed that the jig principle remained in use after hostilities ended. In peacetime production, adjustable fixtures were adapted for railcar frames, bulldozer chassis, and ship sections. By 1947, multiple civilian manufacturers had patented derivative designs based on the original field drawings archived in Detroit. Despite this, Whitaker himself never filed a patent or claimed compensation. The Ordnance Department listed his contribution simply as public service to the United States government. A 1946 technical review by the Bureau of Standards analyzed the broader meaning of the device. It described the innovation as a transition from static tooling to dynamic fixture engineering. That terminology later influenced the standardized methods used in automated assembly during the 1950s. The review emphasized that the concept, not the tool itself, had reshaped industrial reasoning. Factories now viewed every process as adjustable, measurable, and subject to continuous refinement from within. Records from the National Archives show that Whitaker returned to his pre-war position at Great Lakes Steel. His personnel file notes continued employment until 1959, followed by retirement with a modest pension. In a 1951 interview with the Detroit Free Press, he stated, "I just wanted the boys to have more to work with." No official recognition followed beyond a letter of appreciation signed by a colonel of ordnance. The original jig frame, preserved under Inventory Code DTA 117, remained stored in the Detroit Arsenal Museum collection. By the early 1950s, industrial management texts cited the Whitaker case as foundational to lean fixture methodology. It became a reference point for both military and civilian production studies, emphasizing simplicity as a vector of efficiency. Scholars from the Massachusetts Institute of Technology included it in their 1954 study Wartime Production Techniques and Process Efficiency. Their conclusion noted that mechanical adaptability, once demonstrated at scale, established a permanent expectation of continuous process optimization. Measured strictly by outcomes, Whitaker's contribution extended beyond armored warfare. It represented a verified shift in the relationship between labor and engineering. Before 1942, shop workers followed specifications. Afterward, they were recognized as potential sources of innovation. This cultural change endured through post-war reindustrialization, influencing American productivity well into the Cold War era. From a technical perspective, every later iteration of modular tooling traced its conceptual lineage to that simple adjustable frame. In retrospective evaluations conducted by the Ordnance Historical Branch in 1958, the jig was classified as a Category A enabling device. That term applied only to technologies that materially increased combat readiness through industrial effect. In the same classification list appeared radar proximity fuses and synthetic lubricants, both results of formal research programs. The inclusion of Whitaker's workshop invention underscored its extraordinary impact within a field dominated by large-scale science. It remained the only recognized instance of a single craftsman's design altering an entire wartime production system. By official measure, Whitaker's adjustable jig transformed the principle of industrial warfare. It required no factory expansion, no new machinery, and no external material support, only observation and adaptation. Its success proved that efficiency could be engineered as much by perception as by equipment. In the closing analysis of post-war reports, it stood as documentary evidence that the arsenal of democracy was built not solely by machines, but by the ingenuity of the men who operated them. Between 1946 and 1955, the influence of Whitaker's adjustable jig extended into both public and private industry. The War Department's Industrial Efficiency Division conducted comparative studies showing that post-war plants using adjustable fixtures maintained productivity levels 25% higher than pre-war baselines. These gains occurred despite workforce reductions and decreased military procurement. The statistical evidence confirmed that adaptive fixture design had become a permanent element of American production infrastructure. In 1948, the U.S. Department of Commerce issued Bulletin 212, Principles of Modular Fabrication. The opening chapter referenced an operator-originated fixture developed in 1942 that transformed welding throughput at armored vehicle plants. Though Whitaker's name was omitted, the described geometry and data matched the Detroit prototype exactly. The bulletin was distributed to more than 1,200 manufacturing firms transitioning from wartime output to civilian goods. It marked the first civilian codification of a wartime mechanical innovation derived from floor-level observation. In the same period, the Army Industrial College integrated the Whitaker case into its engineering logistics curriculum. Students analyzed the quantitative relationship between process simplification and output elasticity. Graphs reproduced from Ordnance archives illustrated how fixture adaptability maintained steady throughput despite resource limits. By applying the same metrics, subsequent officers managed shipyard and aircraft programs with reduced capital dependency. This instructional practice bridged wartime improvisation and formal production management theory. The Detroit Arsenal retained one of the original jigs for control testing in 1949. Engineers compared it against a conventional fixed fixture under simulated manufacturing conditions. The results remained consistent. The adjustable design yielded 43% shorter setup time and 31% fewer weld reworks. These figures validated wartime reports, confirming long-term durability and reliability of the concept. In technical documentation, the test was logged as Experiment AR93, Endurance Verification, Adjustable Fixture, Whitaker type. Parallel developments occurred overseas. British production experts studying American manufacturing efficiency noted the fixture's influence during post-war reconstruction. The 1950 Ministry of Supply report on U.S. industrial practices cited a manually adjustable alignment frame devised during wartime as exemplary of low-cost process improvement. German industrial engineers examining Allied methods adopted similar jigs for locomotive frame assembly in Essen and Hamburg. By 1952, the principle had been standardized in European welding curricula under the designation Verstelbar-Vorrichtung TYPD. Academic documentation followed. In 1953, the University of Michigan's College of Engineering published case studies in applied production innovation. Chapter 4, authored by Professor Art H. Braden, detailed the Whitaker device using measurements from the surviving Detroit frame. Braden concluded that fixture adaptability functions as a geometric amplifier of labor efficiency. The phrase entered professional vocabulary within 2 years, appearing in trade journals and factory manuals nationwide. Meanwhile, the Office of Technical Services in Washington distributed microfilm copies of wartime engineering bulletins to Allied nations. Among them was Specification E-1057A, the original authorization for the Whitaker jig. It became part of the Marshall Plan's technical assistance documentation, introducing the concept to developing industries in Western Europe and Japan. Translated editions described it as an example of resource-neutral productivity increase through mechanical redesign. Thus, a device built from scrap metal in Detroit influenced industrial modernization on 3 continents within a decade. By the mid-1950s, the original innovation was rarely mentioned by name, but its method had become embedded in global manufacturing practice. Every modular welding line, adjustable press fixture, or jig table for vehicle frames carried its design ancestry back to 1942. In the official summary of the Army's Industrial Heritage Program, issued in 1956, the Whitaker jig was listed under Process Foundations, Arsenal Era. It occupied the same classification tier as interchangeable parts and assembly line sequencing. This position reflected the recognition that adaptability itself had become a form of national industrial power. By 1960, 2 decades after its creation, Whitaker's adjustable jig had become a reference point in both government and industrial documentation. In the Department of Defense's Industrial Mobilization History, 1940 to 1953, It appeared in Appendix 12 under Key Wartime Innovations of Non-Scientific Origin. The entry read, "One adjustable alignment fixture, operator-devised, provided measurable doubling of tank output with zero capital expansion." No other single device within that category was attributed such quantitative effect. Archival correspondence from the War Production Board confirmed continued citation of the jig's influence in post-war mobilization planning. Engineers preparing the 1957 Continuity of Industry Manual included Whitaker's concept as an example of expansion by adaptation. The principle guided contingency procedures for any future national emergency requiring rapid reactivation of idle plants. By maintaining adaptability as a built-in characteristic of tooling, rearmament schedules could be shortened by months. Thus, the concept outlived the factory that produced it, becoming a strategic doctrine rather than a single mechanical aid. Within academia, industrial historians began formal evaluation of its legacy. A 1962 paper by the American Society of Mechanical Engineers titled Operator-Originated Process Improvements in War Industry referenced Whitaker's fixture in its opening section. The study concluded that bottom-up engineering contributions accounted for approximately 18% of measurable production gains during World War II. Whitaker's was singled out as the archetype of field-devised process control. Its continued presence in training curricula underscored the long-term relevance of its underlying logic. At the Detroit Arsenal Museum, curators catalogued the surviving frame for preservation. Inspection reports indicated corrosion, but structural integrity remained intact after nearly 20 years. Visitors noted the simplicity of the device, a rectangular steel frame, adjustable clamps, and threaded bolts. Its unremarkable appearance contrasted sharply with its historical importance. No commemorative plaque was installed, it remained stored under inventory tag DTA 117 in a maintenance annex. Industrial analysts throughout the 1960s drew direct lineage from Whitaker's approach to the emerging field of automated assembly. As machine tools incorporated servo-controlled positioning systems, the same geometric logic applied, adaptability multiplied throughput. The term programmable fixture, first appearing in a 1965 General Motors research report, acknowledged this ancestry implicitly. In interviews with production engineers, many described Whitaker's concept as mechanical flexibility before the computer age. It represented the bridge between manual craftsmanship and systematized automation. Government studies on productivity also retained the case. A 1967 Congressional Subcommittee report titled Technological Lessons from Wartime Industry cited Whitaker's device as an exemplar of unsponsored innovation. The report noted that its enduring influence proved the viability of distributed technical problem-solving across hierarchical organizations. This finding shaped later defense procurement policies emphasizing field modification, rapid prototyping, and adaptive maintenance procedures. By connecting individual observation to systemic improvement, the 1942 jig had quietly influenced federal engineering doctrine. By the early 1970s, few of the original wartime workers remained active. Their recollections, recorded in the oral history of the Arsenal of Democracy project, consistently mentioned the adjustable jig as a turning point. To them, it symbolized a moment when practical skill met national necessity without bureaucracy. Industrial archivists later classified it alongside the Liberty ship welding process and the Jeep chassis assembly line as pivotal wartime efficiencies. Each shared the same defining feature, simplicity leveraged into scale. Measured across 3 decades, Whitaker's invention redefined the meaning of innovation within wartime industry. It demonstrated that strategic advantage could arise not from new factories or machines, but from refined understanding of existing tools. Its success inspired subsequent generations of engineers to view process adaptability as the ultimate form of industrial readiness. Today, within defense production manuals, the underlying formula still appears unchanged: minimal material, maximal throughput, verified by record. From a single jig in Detroit, the logic of mechanical adaptability became an enduring cornerstone of modern manufacturing.